Welcome to Tomorrow Unveiled, where we explore the most groundbreaking advancements shaping our future, giving you the shortcut to being well-informed.
And this week, we're really diving deep.
We're looking at a period that, well, it wasn't just small steps. We saw some truly transformative technological leaps. We're calling it Beyond Earth, this week in space and space tech.
Yeah, our dedicated research team, they've really pinpointed this decisive shift. It's all about foundational capabilities, things that are genuinely extending humanity's reach, our operational capacity beyond Earth.
Right. And what's so interesting, as you said, is how these impacts aren't just up there. They're being felt right here on the ground, changing how we, interact with our own planet.
Big implications.
So to unpack all this, we've kind of identified three core themes, three pillars defining these developments. First up, a revolution in how we see Earth or Earth observation. Then critical advancements in propulsion, how we get around up there.
And stay there.
Precisely. And finally, the emergence of some really novel platforms, new ways to operate in air and space. It's going to be quite the conversation.
Looking forward to it.
Okay, let's kick off with that revolution in planetary insight. Really just feel like we're entering a new age, multi-spectrum 3D observation. And I guess the perfect example is the NASA ISRO NISAR mission. How does that show this shift?
NISAR is, well, it's the poster child for this shift, you could say. Launched July 30th, 2025. It's probably the most significant jump in Earth observation tech we've seen in, decades? And it's not just one agency's project. It's a massive undertaking, a $1.5 billion decade-long partnership between NASA and ISRO. It really showcases what international collaboration can pull off.
And the tech itself is it's incredible. It's got the world's first dual-frequency synthetic aperture radar SAR on one satellite. Can you break down what these two radar bands, L-band and S-band, actually do for us? Why is having both such a big deal?
Absolutely. So NASA's contribution is the L-band radar. Think longer wavelength. The key thing here is it can penetrate through stuffed clouds, thick forests, sand, even ice.
Like an X-ray for the planet.
Sort of, yeah. It lets us measure things we couldn't easily see before, like how much biomass is in a forest, soil moisture deep down, and crucially, really subtle ground movements. We're talking like a centimeter.
Just 1 centimeter.
Yeah, tiny shifts that can be precursors, warnings for earthquakes, volcanoes, landslides. Game-changing for disaster prediction.
Okay, so L-band sees through things and detects tiny movements. What about the S-band from ISRO?
The S-band complements that perfectly. It uses a shorter wavelength, so it's really good at picking up fine details on the surface texture. Think agriculture monitoring crop health, mapping water bodies very accurately, seeing changes along coastlines.
So one sees deep, the other sees the surface details.
Exactly. And because it's radar, it works day or night, rain or shine. So together, L and S-band give us this incredibly rich, multi-layered view. We're moving way beyond just looking at the surface.
And the sheer volume of data, I read it's designed to generate something like 80 terabytes a day, mapping the whole globe every 12 days. That sounds immense. It is immense. 80 terabytes daily is staggering.
Yeah.
But the really fantastic part is the commitment to making all that data freely and openly available.
To everyone.
To the international scientific community, yes. It positions NISAR as this incredible global public good for climate research, managing resources, disaster response. The potential is enormous, even if handling the data volume itself is a challenge. Open access really multiplies the impact.
Okay, so that's NISAR providing this deep multi-frequency view. But just a few days before that, July 26th, Airbus launched its CO3D Constellation. How does that fit into this enhanced observation picture? What's its unique angle?
CO3D is different but complementary. It's a constellation of 4 satellites, and their job is specifically to create and maintain a persistent, high-resolution 3D map of the entire globe.
Yeah, think 50-centimeter resolution imagery, but with 1-meter vertical accuracy. So, while NISAR gives us that deep, penetrating radar view, CO3D builds this incredibly detailed, constantly updated 3D model of the Earth's surface.
And CO3D has some clever tricks too, right? Like this step and stare mode and onboard AI processing. How does that speed things up, getting insights, not just pictures?
That's where it gets really smart. The onboard AI is a big deal. It means the satellite itself can start processing the data, identifying features, say, ships or aircraft, in real time, right there in orbit.
So it doesn't have to send everything down.
Exactly. It drastically cuts down the data bottleneck and speeds up the whole intelligence cycle. And to handle the data it does send, they've got this Ellison optical laser communication demonstrator. It pushes data down at 10 gigabits per second.
Wow, 10 gigabits.
Yeah, that's about 10 times faster than typical systems. So faster data means faster insights, faster decisions.
It definitely sounds like Airbus is playing a strategic game here. Our research team mentioned they're aiming to compete not just on image quality, but on the speed and, well, the dimensionality of the insights, and making it dual use for government and commercial sectors. That sounds like a challenge to the old guard.
It absolutely is. They're building what you could call a vertically integrated data-to-decision pipeline. It sets a new bar for low-latency analytics.
So if we put NISAR and CO3D together, what's the big picture?
The big picture is truly transformative for Earth observation. We're shifting from collecting static images or data points to providing dynamic, multi-layered understanding as a service.
Understanding as a service. I like that.
Together, they're basically enabling the creation of a 4D digital twin of Earth. That's the 3D space we see, plus the dimension of time showing how it changes, the implications strategic, commercial for climate modeling, disaster response, urban planning, defense.
Yeah.
They're just profound. It's like having a living, breathing model of our planet.
It really is incredible stuff. And listeners, if you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and be sure to turn on notifications so you never miss an update on the future.
Definitely helps get the word out.
Okay, so we've got these amazing new eyes on Earth. But seeing is one thing. Getting to space and moving around in space is another challenge entirely. That brings us to propulsion. What's new in the engines powering this beyond Earth push? Let's start with Japan's H3 rocket.
Right, propulsion is key. And it was a big week for JXA, the Japanese space agency. On July 24th, they announced a successful captive firing test for the first stage of their sixth H3 rocket.
That sounds important, especially after they had that launch failure earlier.
Exactly. This test was vital for validating their new main engine, the LE9, and restoring confidence. It's a critical step to getting H3 flying reliably.
And our research team flagged something interesting about the LE9 engine. It uses something called an expander bleed cycle. First time for a first-stage engine, apparently. Why is that significant? Sounds technical.
It is a bit technical, but the payoff is pretty straightforward. Basically, the expander bleed cycle allows for a simpler engine design. Think fewer complex parts, like pumps running under extreme stress.
Okay, simpler means more reliable, cheaper.
Both. Increased reliability and significantly lower manufacturing costs. And that's crucial for JAXA. The whole point of the H3 program is to give Japan a competitive edge in the global launch market.
So competing with SpaceX, Ariane, etc.
Precisely. But it's also about ensuring Japan has its own way to launch important satellites for science, for civil use, and for national security. Sovereign access to space is a big driver here.
Makes sense. Self-reliance in space. So that's the big picture heavy lift launch. But then there's the other end, the small satellite revolution. Our team highlighted a new, compact electric propulsion thruster from Moog. Why is that such a big deal?
Yes, electric propulsion, or EP. These are the super-efficient, low-thrust engines that are really enabling the small satellite boom. They sip power and propellant, allowing small sats to maneuver precisely for long durations.
Without needing big fuel tanks.
Exactly. And this new Moog unit, introduced in July, is apparently about 20% more efficient than previous models. Plus, it's modular, designed to easily plug into standard CubeSat or NanoSat platforms.
So easier integration for satellite builders.
Right. And these systems are just fundamental for the huge low Earth orbit, or LEO, constellations we're seeing. They need EP for everything. Raising their orbit after launch, staying in precise formation, dodging debris in increasingly crowded space.
Collision avoidance is becoming huge, isn't it?
Absolutely. And also for responsible end-of-life disposal, making sure satellites deorbit safely instead of becoming more space junk.
So these little EP thrusters, they really punch above their weight in terms of impact. It sounds like they changed the whole economic equation for constellations.
They totally do.
Yeah.
Better efficiency means you can either pack more operational satellites onto a single rocket launch, which cuts costs, or you can give each satellite more payload, more capability for the same mass. It fundamentally alters the business case. It's a key enabling technology for this whole LEO economy.
Really democratizing access in a way.
You could say that, yeah.
And for those of you listening on audio platforms like Apple Podcasts or Spotify, if you're enjoying Tomorrow Unveiled, we'd be incredibly grateful if you could leave us a rating and review. It genuinely helps new listeners discover the conversation.
It really does.
Okay, let's pivot now. We've talked observation, we've talked propulsion. Now let's get into some truly novel platforms and this idea of making things in space. This feels like where the future gets really interesting.
I agree. And a great example is Regentcraft. They're a U.S. startup, and this week they launched a new defense-focused unit. They're adapting their all-electric sea glider technology for military use.
Sea gliders.
Right.
Those are the wing and ground effect things, right? They fly just above
I
the
for
water.
them, wake vehicles. Flying on that cushion of air dramatically cuts down aerodynamic drag, making them incredibly efficient compared to regular aircraft flying higher up.
Such a cool concept. And Regent's big innovation is adding hydrofoils. How did that help? I remember older wing designs had issues.
They did, especially with takeoff in choppy water. The hydrofoils lift the hull out of the water before it starts flying in ground effect. This makes takeoff much smoother, more stable, more reliable.
Smart. And the performance.
Pretty impressive. Their main model, the Viceroy, can apparently hit 160 knots. That's pretty fast, with a range of 160 nautical miles, all electric. And they have a hybrid option that pushes the range out to like 1,400 nautical miles.
1,400 miles. That's significant reach. And they have a smaller autonomous one, too.
Yeah, the Squire, designed more for surveillance, light logistics. Our research team thinks these sea gliders fill a really interesting operational gap, especially for defense.
What kind of gap?
Think rapid, relatively stealthy movement in coastal areas, what they call littoral environments. For logistics, getting troops in or out quickly, intelligence gathering. They're fast, fly super low, often below radar detection altitudes, have low signatures, and don't need runways.
So faster than a boat, stealthier than a helicopter or plane in some ways.
Exactly. They bridge that gap between slow sea transport and expensive, more visible air transport, particularly in contested zones.
Fascinating. Okay. From just above the waves to low Earth orbit, manufacturing in space. The European Space Agency, ESA, and Airbus announced they 3D printed the first metal part on the ISS. Why is metal printing such a hurdle compared to, say, plastic?
This is a really significant step for what's called ISEM in space servicing, assembly, and manufacturing, basically building and fixing things in orbit.
Right.
We've been 3D printing polymers, plastics on the station for years, but metal is much harder. You need much higher temperatures, very precise control, and managing the molten metal in microgravity without it just floating off. It's complex.
I can imagine.
So successfully printing a metal part is a major proof of concept. It shows we're developing the capability needed for a much more ambitious goal.
Like long trips to the moon or Mars, being able to make your own spare parts.
Exactly. Imagine being on Mars and needing a specific tool or a replacement part for critical equipment. Printing it on demand instead of waiting months or years for a resupply mission from Earth. That's transformative.
It totally changes the logistics. Reduces the sheer amount of stuff you have to launch initially.
Dramatically.
Yeah.
It cuts down the huge cost and complexity of launching every single screw, bracket, and tool from Earth. This is foundational for building self-sustaining bases, commercial space stations, maybe even orbital factories someday. It's a cornerstone for long-term human presence beyond Earth.
Science fiction really becoming science fact there. Okay, so we've covered some incredible progress. NISAR, CO3D, H3, compact EP, sea gliders, metal printing. But, progress always comes with challenges. What are the main hurdles our research team sees accompanying these leaps?
Well, one big one is simply the crowded skies problem, especially in low Earth orbit. All these new mega constellations are amazing, but...
More traffic means more risk.
Exactly. The sheer density increases the chance of collisions. And a collision could create debris, which causes more collisions.
Oh.
That's the Kessler syndrome nightmare scenario.
Right, the cascading failure.
Plus, all these satellites need to talk, so there's intense competition for a limited radio frequency spectrum. And the reliance on satellite navigation, like GPS, makes these systems vulnerable to jamming or spoofing. Managing LEO is getting really complex.
Space traffic management is going to be huge. What about just the sheer difficulty of building this stuff?
That's what our team calls the engineering gauntlet. Even for major space players, developing a new heavy-lift rocket like Japan's H3, or integrating incredibly complex instruments like NISAR's dual SAR, it's still incredibly hard.
Takes years, billions of dollars, huge teams.
And lots can go wrong. These projects involve pushing the boundaries of physics and engineering, and success is never guaranteed. Long lead times and high risks are still very much part of the game.
And we touched on this earlier, but there's a geopolitical angle too, right? With all this data from space.
Definitely. The geopolitics of data, you see this tension playing out. On one hand, you have amazing international collaboration, like NISAR making its data open for global science. That's fantastic.
On the other hand.
On the other hand, nations and blocs also want strategic autonomy. Look at Europe's CO3D constellation. A key driver there is having their own independent source of high-res geospatial intelligence. So space data is both a tool for global good and a strategic national asset. It's a tricky balance.
Yeah, cooperation versus competition. And lastly, for those really new things like the Region Sea gliders, do the rules even exist yet?
That's another challenge. These novel platforms often operate in a kind of regulatory gray area. Is a sea glider a boat? Is it an aircraft? It's sort of both and neither.
So maritime law or aviation law,
Yeah.
something new.
Exactly. We need clear, internationally agreed upon rules for how to operate them safely, how to certify them, how they interact with existing sea and air traffic. That regulatory framework needs to catch up with the technology for them to really take off commercially.
Lots to navigate, technically and politically. Okay, despite those hurdles, what's the overall outlook? Where are these trends heading?
Well, the global launch market is definitely going to keep shifting. We'll see players like Japan with H3 pushing hard for that guaranteed sovereign access, trying to capture market share from the current leaders. More competition, hopefully driving down costs.
And those little EP thrusters.
Compact electric propulsion will just continue to be a massive enabler for the whole new space LEO economy. Expect bigger, more capable constellations fueled by that tech.
What about the Earth observation side, the 4D digital twin idea?
That persistent, high-fidelity 3D global mapping, like from CO3D, I think that moves beyond just niche government or scientific uses. It becomes foundational infrastructure.
Like roads or the internet?
Kinda, yeah.
Yeah.
Think smart city planning, optimizing 5G and future 6G networks, risk assessment for finance and insurance sectors. Autonomous vehicle navigation relies heavily on up-to-date 3D maps, plus all the critical climate science applications. It becomes ubiquitous.
And the sea gliders. Niche or mainstream?
Probably a strategic niche initially, especially for defense logistics in those tricky coastal areas, filling that specific gap between slow ships and expensive aircraft. But who knows where the tech could go long term?
It really feels like these developments aren't just isolated breakthroughs. They're interconnected, driving this whole ecosystem forward.
Absolutely. This week really underscores that decisive shift, how we see our planet, how we get to and operate in space, even new ways to move across our oceans. They're all feeding into each other.
Laying the groundwork for, well, for a very different future. New value, new ways of operating, new strategic realities.
Exactly. The impacts of what's happening now will be felt for decades. They're fundamentally reshaping things. It's an exciting and challenging time to be watching this space.
It certainly is. And we love hearing your thoughts on all of this. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this week's breakthroughs in space and space tech. What excites you the most? What challenges worry you?
Yeah, join the conversation.
This is Tomorrow Unveiled. And the future, as we keep saying, is unfolding right before our very eyes. Thanks for tuning in.